Buenas. Bueno, vamos a comenzar con la siguiente sesión. Professor Paul?
Yes, I'm there.
Yeah, you're here?
Yeah.
Perfect. So, sorry, just to, because I need to, okay, yeah. So, we want to present the talk from Professor Paul Nuiro, and he's professor in the University of French West Indies since 2018, and he's a professor in applied mathematics and specialization in PDs. So he will present the talk about COVID-19 database approach using a multi-group SIHR model with fuzzy subsets. Go ahead, Professor.
Okay, thank you. I will share my slide first. Did you see my slide? It is okay?
Yeah. Maybe you can make it full screen?
Yes, yes. Yes. Thanks, thanking the organization for inviting me to speak today. So I will speak about COVID-19 as is the session theme. So in our work, because it's a joint work with 3 other co-authors, my FIDI student Woody Mera, Professor Donchescu, a computer science professor, and Sébastien Régis, who will also be a doctor in computer science. So in this work, we use a multi-group SIHR model to simulate the spread of COVID-19 in an island context, because Guadeloupe is an island, an archipelago of islands, more precisely. The multi-group aspect enable to modelize transmission of the virus between non-vaccinated individuals within age group, as well as different age group. In addition, we put fuzzy subset and aggregation operator to taking into account the increased risk associated with age and obesity within different groups. In a conceptual point of view, we model the emphasis of the notion of hospitalization, which is a major point of this pandemic, by replacing the removed compartment by hospitalization compartment. We have results using medical and demographic data, special from Guadeloupe, and the results show that without respect of barrier gesture, we could find a first wave very deep for all the category, but we also see a second wave appearing after. So I will try to explain the process of this research. So let me move there is a problem with the Okay, donc my outline stand in 4 points. First, I will introduce, in my point of view, the problem. And after, I will explain the method used, and I will show some results, and after, some conclusive remarks. So in this pandemic, the first thing we have to point out is the very quick spread of and the severity of some form of the virus. And after, in all the country, we have a devastating pandemic. So there was a very big problem to deal with, and we saw a lot of deaths, a very big amount of deaths, and a lot of people in the intensive care unit. And in the first wave, without no measure to control the evolution of the pandemic, every government, every country has problem to deal with the pandemic. So there is a lot of measure causing problem in economic point of view or social point of view. So the reaction in managing the crisis is to first try to develop treatment, vaccine, for example, or drugs, but also to develop simulation and prediction. There is a prediction to help in the decision process making to deal with the crisis. So it appears more quickly that the big problem is the hospitalization, and to control the hospitalization, because all the hospital has been in overflow, and they don't know how to deal with all the patients coming to the hospital. So we decided to bring something in the process to try to model COVID-19. And we see in the literature most model are from SIHR types or extension of it. And we decide to do the same. But in fact, there is also another things to take into account is the risk factor, because quickly the doctors, the medicines men, so that age is a big factor, but also comorbidity as or obesity or things like that. So we try to put this ingredient in our model. So let me develop the methods. So first, as I said, the multi-group SIHR approach to this kind of approach has been developed, for example, by an author like Magal in 2018, and with two age group, but we decide to adapt it for our population with 3 age group. I will develop that later. Young people, it's about 0 to 20 years, 30 years, excuse me. Adults from 30 to 60, and elderly over 60. But we want also to introduce, as I said, obesity as a aggravating factor in addition to age factor. And we assume that no population, there is no transfer of population between the age group. So the fuzzy aspect of the model. Fuzzy subset permits to give a sense of reality in the simulation, because everybody knows there is a random part in the evolution of the pandemic, and no one can predict exactly what's going to happen in the next step. So it is interesting to try to introduce this random part, but we did it with a fuzzy subset, and we did it with a fuzzy membership function to model the risk of having a severe form of COVID-19 by using age function and obesity function too. So let me present the model that we use for our simulation. So it's a simple SIHR model with, as I said before, we replace the remove compartment by an hospitalization compartment, but we also put in this model the fact that there is transmission of infection between the different age group. And we also introduce in this coefficient, y indexed by I, the fact that the hospitalization has a random part. Okay. So just some presentation of the model. So S1 is a number of young potentially ill subject. S2 is the same for adult. S3 and S3 is elderly. But usually the index 1 is for young, the index 2 is for adult, and the index 3 is for elderly. Okay. Okay, let me. So this picture is here to show you how we conceive the relation between the group of youth and adult. You see, we have the compartment of susceptible for young people, the compartment of susceptible for adult people. We have this arrow show you the possibility of infection of young by young, so intra-group, but and the same for the adult. But we have an arrow here which symbolizes the infection by young by adult, you know? And the same for adult by young. And here we have the possibility, the probability of infection, not infection, the probability of going to hospital, which is model with a fuzzy element. And we can do the same picture with the other couple of categories. So we have to calculate the intra-group coefficient rate, but we have data and we conceive it as a time series. When we start to fit the model, we have data from 2020 and in the first part of 2021. So we have also to calculate intergroup infection rate. And we do this from real data of evaluation of number of cluster in the population. We will come back to precise the value after when we will go to the results. Here it's a curve of incidence rate by age group in Guadeloupe. The brown is the adult, usually the deeper rate. The green is for the elderly and the blue is for the youth. Okay, I move. And yes, I will introduce the fuzzy subset and the fuzzy parameter. So first I have to recall, but it's a simple mathematic process, the characteristic function, and a fuzzy subset B is defined as a membership function, which associate to each element X of a big X space, a degree f of x between 0 and 1, which with which x belong to B. So we will see. Yes, but as I will say, a first example of kind of function can be the probability distribution function of uniform law, for example. So yes, so we use for the age the first membership probability distribution function. You see 0 from 0 to 13, a portion of for 30 to a proportion for 30 to 16, and 1 for over 60. And the problem is I can't control this, I guess. But for obesity, it's not the same because we have two functions, one for the woman, one for the man. Because in the statistic of the Public Health France agency, they have so that the woman goes to obesity before the man, because the woman it starts about 35 years and goes up at 45 years. And for the men, it takes more time. It starts to 35 also, but it goes up at 55. But we have two probability distribution function for obesity. So we have to reduce to one value. So we take a weight average using weight coming from public health funds. It shows that for the men, the weight is 0.6, and for the woman, it's 0.4. And using this weight average, you have one value for one function value for obesity. And we have now a function for age risk and a function for obesity risk. So we have to merge the two in one function to have one coefficient. So usually we take the arithmetic mean, which is a compromise between the max and the mean. So we can also use what they call a triple P operator, introduced, for example, by Emilion in 2013. This is a reinforced operator. This provides a value which emphasizes the positivity and with emphasis which emphasizes positively the value or negatively the value. So this is the one expression of the triple P operator. We can choose the large of possibilities. So we use this one. You know, when the max is strictly under 0.5, we use the mean with same weight. When the mean is strictly over 0.5, we use this expression. And in the other case, we will use this weight mean with 7 for the max and 3 for the mean, and all over 10. Okay. So we assume that each person has the same chance of catching the virus. So this leads us to use a uniform distribution to model the probability of catching the virus with chance to go to the hospital. And the continuity of the FUSI membership allow to simulate the value of hospitalization rate using one of the two aggregation operators. This results of an hospitalization rate for each free age group. So we will go to show some results. So I will present the data used. So we use the real value of the population in Guadeloupe in the three first compartment of susceptible. This data is provided by INSEE Guadeloupe. This is the National Institute for Statistics and Economical Study. It's a national agency, and there is a little part in each part of its region of France. And with one person infected in the category of adult. So the coefficient of infection of first, the coefficient of hospitalization, as I said just before, is the result of the fusion of the FUSI value. The coefficient of infection intragroup takes this form with K normalization constant and Ri with incident rate as a time function for each group A. So we have also the infection rate intergroup. So E is different of J. And this is a project of two numbers. First, a normalization constant, and C, the data on cluster infected provided by Public Health France. So we use a simply Euler method to solve the system, the differential system, which is I don't know, I can say nothing because this use a very easy method to implement. And we use it on a computer with a 3.6 gigahertz. Let's go. So we use a mapper software to program, to implement our program and to make the computation. So let me show you some curve. So the first curve is we have the curve of infection for the youth and the curve of hospitalization. The blue one is infection and the brown is hospitalization. So this is surprising because the problem is first, we do not have any data for the infections of the youth because in our country at the beginning of the crisis, there is no test for the young people and no, because they said there is no attempt for the young people to get the virus, and after they said they are asymptomatic, but in fact there is no real good statistic from the infected young people. But in fact, in the hospitalization is not also significant because, as I said, they said the young people doesn't have any risk, so they don't have to go to the hospital. They stay at home and they wait. The things go by. The same curve for the adult, and we will see a deep increase of the infection about 150 days and a maximum at about 160 days. And we see there is a decreasing and after a little increasing too. But we also see here that there is another increasing, a little increasing. And we see the curve of hospitalization is going very, very deeper to the maximum with something, a period of calm and another augmentation, another increasing. The same for the elderly. So we see increasing, decreasing, a second increasing, and hospitalization going up quickly. All the previously curve has been done with the mean as a fuzzy aggregation operator. Let me show you the free infected curve in the same picture. And you see the second wave appear first for the adults and after for the elderly. So we can conjecture that the adult has transmitted something to the elderly, but it's just a conjecture. The hospitalized curve in the same picture. So you see first the adult and after the elderly and in last the young. But as in Guadeloupe, the young people are very numerous, so the increasing of hospitalization, I think, take into account the fact that there is about 2 times more young than elderly people. So here's the infected curve, but with the triple P operator, the curve for the young and the elderly is about the same, but the curve for the adult is very different with with oscillation and in this part, and but we also see the second wave for the two in the same order. And I didn't put the other picture because they are widely the same as what I have presented for the mean operator. So just a picture to see how the hospitalization rate evolve in time. So for the elderly, we have a constant value about 0.95. For the young, constant value about 0.05. And for the adult, we have a very oscillating value, but it seems that the mean is about 0.5, which is the weight, the weighting value, because we use a uniform law over 0.1. So we also make a comparison between the simulated value and the real data. So for the youth, at day 140, we have 18.5%. In the real data, we have 3.4%. For the adult, we have 29.4%. And for the real data, we have 31%. And for elderly, we have 52.1%. In the real data, we have 65.6%. But we see there is a big gap between the value of the simulation and the real for the youth and for the elderly. But for the adult, the value are not equal, but closer, because there is only less than two points of difference. And remember, for the adult, this is where the fuzzy coefficient are very acting. The real data is provided by the ARS, the national, the regional health agency. So to conclude some remarks, but multi-group SIHR model using fuzzy inference, real data from Guadeloupe, replacing removed by hospitalization, using a fuzzy set to model, to activate the plasticity of the model. But the most important thing is the fact that the model is well suited for Guadeloupe, because in Guadeloupe, the three age groups are living usually very close. They have contact all days, etc., because they're living very, very close. This is different, for example, if you are in the region of Paris, you have the elderly are living far away from the adult and the young. But in Guadeloupe, it's very different. You have very close situation for all the three groups. So there is an impact in the contamination. A limitation, the fact that the value are very different for the youth and for the elderly. And but in fact, all the results show the very deep increasing of infection, because as I said before, our model didn't directly taking into account the fact that there is a curfew, social distanciation, or all the measures that the government take to control the spread of the virus. So I will just show you some references. But this is the paper published with this work in biology, and I just put in like 3 other references you can find in the bibliography of this paper. But this one for the SIHR model, and these 2 for the fuzzy part. So this is the end. I thank you for your attention. Gracias por su atención.
Thank you very much, Professor.
And the 2 is in French and in Creole, the 2 others.
In Creole. How do you say in Creole?
Merci pour écouter Azot.
It's very close to the French.
Yes, because Creole is the last part of all French.
Okay, so is there any questions? Well, I have a question, but it's not for me, it's from Agustin Gomez. He just left because he has something, but he's asking me, I'm going to make a real-time translation, so sorry for, but he asking me, if you did analyze the symptomatics in the young people, the
young
persons, people? Yeah, because the nature of the virus tends to incite less in the youth than in the adults. So he asked if the models can be affected by the incidence in the youth people against the adult populations, and if you take account this kind of difference between youth and adults to make your predictions, and if you use some probability for this for those variables, or what mechanism do you use for difference the youth and the adults regarding the incidence of the virus in each population?
Okay. Yes. Thank you for the question. The young people is a problem for us because in Guadeloupe we have a lot of obese young people, for example. So it's not the same in certain countries, but for example, in the US, there is a part of population with a lot of obese young people. So we didn't take this into account first, but effectively we have an idea of work to study the part of the obesity in the evolution for the young people. But in this model, we didn't take it into account. Okay, so it may explain the fact that there is a big gap between the real value and the simulated value.
Okay, perfect. Javier, just a quick question, please, because the time.
Yes, thank you very much. I think it is a very good idea to use fuzzy sets in this modeling. As long as I understood, you model the fuzziness with the factor of obesity, the risk factor of obesity. Maybe the gap with young people and elder people is that the fuzzy model itself for obesity in that populations is not as good. For example, in Costa Rica, there is a population of young people, very young people with obesity, and in Mexico also. So maybe the model itself in the fuzzy model of is there the origin of the gap for young people and maybe for elder people, because elder people also tend to diminish the obesity after a certain age. So maybe there you can adjust a little bit your model. And another question is not a real question, but maybe some work for the future, because there are some other risk factors such as diabetes, asthma, and how could you handle two risk factors with this fuzzy model, for example, diabetes and obesity?
Thank you, Professor Trechus. I can say first, there is no conceptual problem to include another risk, because we can use the fuzzy operator with 3, 4, 5, whatever you want. Okay, even you have to be able to produce the membership function. If you can include it in the model. For the other part of the question, effectively, we use the uniform law for all the people, but I agree with you, the fact that for the young people, this is not a uniform law we can use, because young people has a risk decreasing with the age. So each young people doesn't have the same chance to catch the virus. And for the elder, it's the inverse problem, because when the age grows, the risk decrease. So this is a possibility for the future works. I agree with you. But
thank you.
In the moment, we are working on completing the model by the remove and the death, and taking into account the vaccination, and try to make some optimal control also over this parameter.
Okay.
Thank you.
Thank you
very much. Thank you very much. Okay, bueno, vamos a, tal vez en español, vamos a empezar con la siguiente presentación del profesor Roberto Molina Cruz. Si está...